Let's start. Today we will discuss about random variable. In our previous class, we start with the definition of probability and experiment is said to be random when it satisfies three conditions. All possible outcomes are known in advance. This was the first condition. And the second one is it impossible to predict which outcome occur at a particular performance? And the third one is it can be repeated. The experiment can be repeated infinite number of times. If the three conditions hold for a particular experiment, then we said that the experiment is random experiment. And we said that the outcome of a random experiment is an event. And the set of all events is the sample space or event space. That was denoted by capital S. Sometimes we are not interested in knowing which of the outcomes has occurred, but in the number associated with them is interesting or calculating to us. Sometimes we are interested not in knowing which of the outcome has occurred, but in the number associated with them. For example, when two dice are thrown, we seek information about the sum of points and not really concerned with the separate number on each face. Thus, we associated a real number with each outcome.
এক্সকিউজ মি স্যার
Hello?
স্যার আপনার আওয়াজটা খুব কম আসছে স্যার
এবার শোনা যাচ্ছে?
স্যার আর একটু বাড়িয়ে দিন স্যার একদমই খুব আস্তে আস্তে শোনা যাচ্ছে মানে
কিন্তু আমি ফুল ভলিউম দিয়ে রেখেছি। এবার শোনা যাচ্ছে?
হ্যাঁ স্যার স্যার আপনি না একটু রেকর্ড করে নিন না, যদি কিছু নাও শুনতে পারি তাহলে পরে একটু শুনে নেব।
এখানে কোনো অপশন আছে রেকর্ড করার?
হ্যাঁ আছে স্যার।
কোথায় বলো, আমি জানি না অ্যাকচুয়ালি। হ্যালো?
স্যার ওই প্রেজেন্টেশন অপশনের পাশে দেখুন তিনটে ডট আছে, ওই ডটটায় ক্লিক করলেই আমি অপশনটা পেয়ে যাবেন।
এখানে রেকর্ডিং অপশন করতে পাচ্ছি না আর কি। মেবি
সেটিংসটা একবার খুলে দেখতে পারেন স্যার। না নেই।
নেই। শোনা যাচ্ছে? ভয়েস শোনা যাচ্ছে এবার? হ্যালো?
স্যার ওই কোনো মতে স্যার, খুব একদম ধীরে ধীরে স্যার।
কিন্তু আমার তো তবে তোমাদের কথা কোনো আমার কানে প্রচন্ড লাগছে আর কি। হ্যালো, এবার শোনা যাচ্ছে?
স্যার শোনা তো যাচ্ছে কিন্তু খুব কম কম আওয়াজটা।
স্যার আপনি নিজে একটু ভয়েসটা বাড়িয়ে কথা বলুন, তাহলে হয়তো ভালো শোনা যেতে পারে।
ঠিক আছে, আমি তো জোরেই বলছি। ঠিক আছে, চেষ্টা করছি। আগেরগুলো কি রিপিট করতে হবে আমি যেগুলো বললাম?
স্যার একটু করলে ভালো হয়।
ঠিক আছে। Today we will discuss about random variable. In our previous class, we said about random experiment. An experiment is said to be random when it satisfies three conditions. condition 1 was all possible outcome are known in advance. It is impossible to predict which outcome will occur at a particular performance. It was the second condition. And the third one is the experiment can be repeated infinitely many number of times. And we said that the outcome of a random experiment is called an event. And the set of all possible outcome is called sample space or event space. Sometimes we are not interested not knowing which of the outcome has occurred, but in the number associated with them. For example, when two dice are thrown, we seek information about the sum of points and are not really concerned with separate number of each face. Therefore, we associated a real number with each outcome of an experiment. Such a real valued function is called a random variable. Now the definition of random variable. If even random experiment and S be its event space and delta be the sigma field. What was the definition of sigma field? A class delta is said to be a sigma field on S if the whole set S belongs to delta. The second condition was if a event A belongs to delta, this implies a complement belongs to delta. And the third condition was if A1, A2 infinite number of events, countable infinite number of events belongs to the class delta, then their union also belongs to delta. If these three conditions hold, then we said that the class delta is a sigma field or Borel field on S. The definition said that if delta be a sigma field on the event space S, a mapping X, the S to R, that is sample space to real number, is called a random variable if the inverse image under X of all semi-closed interval of the form minus infinity to X. Semi-closed means one side is open and the other side is closed. The mapping X is said to be random variable if the inverse image under X of all the semi-closed interval of the form minus infinity to X are belongs to that sigma field. That is X inverse minus infinity to X belongs to delta, where W is an event, where XW belongs to minus infinity to X. This is the definition of random variable. Therefore, a random variable is a mapping from the event space to R. That is, X is a real valued function on S, the event space. If the condition hold, that is the inverse image of all semi-closed interval of the form minus infinity to X, X belongs to R, real number, this belongs to the Borel field delta, then X is called random variable on S. The range of the mapping X is called spectrum of the random variable. If the spectrum of the random variable is discrete and maybe discrete and continuous, if it is discrete, then the random variable is said to be discrete random variable. If the spectrum is continuous, then we said that the random variable is continuous. Here note that the random variable does not depend on does not directly related on the event E. It is associated with S and the Borel field delta. Here x is not a variable, it is a function, a real valued function. Also, x is not a random. X assign a real value and assign a value to the outcome W of the sample space S. W is random. Then why x is said to be a random variable? X is not random. It is a real valued function which assign a real number to all the outcomes of the sample space. For example, if the experiment is tossing a coin, then the sample space is H and T, and we define a real valued function in this way that the x be defined by number of heads in the outcome W. X be the function that define the number of head in the outcome W. If the outcome is H, then the function assign number 1 for H, and if the outcome is tail, then the real value function assign 0 for tail. Is it okay? In this situation, x inverse minus infinity to x, that is inverse image under x from minus infinity to x. If x less than 0, then there is no event in this interval. Then x inverse minus infinity to x is equal to 5. That is impossible event. If x belongs to 0 to 1, then there is a event which is t. That is, this happen as xt is equal to 0 and t belongs to that interval minus infinity to 1. Here what we said about interval is semi-closed interval, whose left side is open and right side is closed. If x greater equal to 1, therefore there is 2.0 and 1 for the values of x. That is, it is the whole event. This is why x inverse minus infinity to 1 or greater equal to 1 is equal to the whole space, sample space, that is H and T. Is it clear? We say that random variable is a real valued function from the event space to R. Here the event for this example, when we tossing a coin, the sample space is H and T, and we define the real valued function or random variable x by number of heads in the outcome W. Therefore, x of h is equal to 1 and x of t is equal to 0. We define this x. We have to prove that this is a random variable. To prove this, that x is a random variable, we have to say that the inverse image of any semi-closed interval of the form minus infinity to x belongs to that class del. Del is the Borel field, which is the set of all possible subset of the event space S. Here, when x less than 0, then x inverse minus infinity to x, there does not contain, this interval does not contain any values of x, capital X, because the values of the range of the random variable is 0 and 1 only. And when x inverse minus infinity to x, when x less than 0, then the event is there is impossible event. Therefore x inverse minus infinity to x is equal to 5. If x belongs to 0 and 1, then it will be t, and when x greater equal to 1, then x inverse minus infinity to x is equal to h and t, that is the whole sample space. Okay, if we toss 2 coins, then the outcome contain 4 sample point, here denoted by W1, which is HH, W2 HT, W3 TH, and W4 equal to TT. This 4 sample point, and we define a map X S to R as follows: XW is equal to K, where K is the number of head. That means X of W1 is equal to 2, X of W2 is equal to 1, X of W3 is equal to 1, and X of TT is X of W4, that is TT is equal to 0. Because in the event W4 there is no head, this is why X of W4 equal to 0. We define the X, but if this mapping is a random variable, then it has to be proved that the inverse image of any semi-closed interval of the form minus infinity to x belongs to the Borel set or Borel field on S. Now my question is, which is what is the event where that is when x less than 0, that is what is x inverse minus infinity to x when x less than 0? Hello? Can you hear me?
Yes, sir.
Can you answer this? What is x inverse minus infinity to x when x less than 0?
It's an impossible event.
Impossible event. When x belongs to 0 to 1?
A probable event.
What?
Any probable event which can occur actually.
No, actually, which event?
Head.
Hello? when x belongs to 0 to 1, that is 0 less or equal to x less than 1, then the values of x in that interval is 0 and 1. For the values 0, which is the event? The event is tt. Okay, therefore minus if x inverse minus infinity to x when x belongs to 0 and 1, the event is tt. When x belongs to 1 to 2, then in this range, in this interval, the value of p are 0, 1. The corresponding event is tt, th, ht, that is w1, w2 and w2, w3 and w4. If x greater than 2, then the interval minus infinity to x contain all the values of x, that is 0, 1, 2. These are the 0, 1, 2 is the range of the random variable x, which is called spectrum. Therefore, this interval contain all possible outcomes. Therefore, the corresponding event is the whole sample base. This is why x inverse minus infinity to x when x greater equal to 2 correspond the whole event space, that is tt, ht, th and hh. Can you understand?
স্যার
Okay, হ্যাঁ,
স্যার বলছি যখন এক্সটা 1 এর থেকে বেশি হচ্ছে বা ইকুয়াল হচ্ছে তখন টিটা কেন থাকছে? তখন শুধু
বলতে
এইচটি আর টিএইচ হবে।
না, আমরা অ্যাকচুয়ালি ইন্টারভ্যালটা নিচ্ছি মাইনাস ইনফিনিটি টু এক্স, যখন এক্সটা যখন 2 এর চেয়ে কম বলছি, তখন টি কোন কোন ভ্যালু নিচ্ছে? আমরা তো ইনভার্স ইমেজ বার করছি না।
আচ্ছা আচ্ছা, মাইনাস ইনফিনিটি থেকে নিচ্ছে।
হ্যাঁ,
রাইট
মাইনাস
রাইট
ইনফিনিটি থেকে নিচ্ছি আমরা ওখান পর্যন্ত, 2 পর্যন্ত নিচ্ছি, 2 এর আগে পর্যন্ত আর কি, জাস্ট। তাহলে 0 আর 1 কে কন্টেন্ট করছে।
হ্যাঁ, 0 নেবে 1 নেবে।
তাহলে আমি যদি ওর প্রি ইমেজ বার করতে যাই, তাহলে কোন কোন ইভেন্ট গুলো পাচ্ছি আমরা? 0 এর জন্য ইভেন্ট আসছে আমার টিটি, আর 1 এর জন্য ইভেন্ট আসছে এইচটি এন্ড টিএইচ। ক্লিয়ার?
ইয়েস স্যার।
এখানটা বোঝার চেষ্টা করো, বাকিটা কিন্তু এগুলো এই কনসেপ্টটা বারবার আসবে আর কি, সেই জন্য এতটা ডিটেলস আমি চেষ্টা করছি আর কি। যাই হোক, for this experiment, the random variable, the spectrum of the random variable is 0, 1 and 2, which is range of x. According to our notation, x is equal to 0 means, actually x is equal to 0 means x of the event for which x assign the value 0. This represent tt. When x belongs to close interval 0 to 2, then the interval minus infinity to x contain all possible values of x. Therefore, this is the certain event, and if x belongs to 1 to 2, in this interval x does not contain any values, therefore it is an impossible event. Okay, there is another example. If we consider the sample space is 1 to 6, that contains 6 elements. Now we define a function on S by x of w is equal to 1 when w is even. W is the actually outcome or events, and xw is equal to -1 if w is odd. We define this x to prove this x is a random variable on that sample space S. Then we have to prove that all possible semi-closed interval minus of the form minus infinity to 0, the inverse image belongs to the Borel set, or sorry, Borel field. Therefore, we have to show that x inverse minus infinity to here the range of x is -1 and 1. Therefore, to show that this is a random variable, we have to show that x inverse minus infinity to x when x belongs to I, that all the inverse image belongs to the Borel field delta. When x less than 0, when x less than -1, then x inverse minus infinity to -1 is equal to 5, because there is no point in that interval. If x belongs to -1 less or equal to x less than 1, then x contain the value, then the interval contain the values of x -1. Therefore, x inverse minus infinity to x in the interval when x belongs to -1 to x is equal to the event 1, 3, and 5 as x of w for w equal to x equal to x inverse minus infinity to x when x belongs to -1 to 1 is equal to 1, 3, and 5. There is this here, and if x greater equal to 1, then the interval contain all the sample point. Therefore, x inverse minus into x is equal to s. So x is a random variable. We can prove this as it satisfies this condition. Is it clear what is random variable? Here is a theorem. Actually, this is about the some properties of a random variable. We know that function from a sample space S to R when x inverse minus infinity to x belongs to the Borel set. What is x inverse minus infinity to x? Is equal to that event, that is w belongs to S, such that xw belongs to minus infinity to x, that is minus infinity less xw less or equal to x. If this happens, then we said that the real valued function x is a random variable. The second one says that if x1 and x2 are two random variable, then their sum x1 plus x2 is also a random variable. Scalar multiplication, that is if alpha is a real number, then alpha x1 is also a random variable, and x1 dot x1, the product of two random variable is also a random variable. 3 says that mod x is also a random variable. Similarly, square root of a random variable is also a random variable only if the random variable does not take any non-negative value. And 1 by x is also a random variable if xw not equal to 0, that is there does not exist an event w belongs to s such that x assign the value 0 for that variable. If there does not exist that event, then 1 by x is also a random variable. And minimum of two random variable is also a random variable. Similar for maximum. If g r to r, where r is a real number, is a continuous function and x is a random variable, then g of x is also a random variable. These are the properties of random variable. We need not have to prove these properties. Now we discuss about distribution function of a random variable. What is a random experiment? Then we define what is event space, what is an event, and on the event space we define a real valued function said random variable. Now we define the distribution function of that random variable. Let S delta and P. S is the sample space, delta is the Borel field, and P is the probability. The triplet is said to be probability space. If let S, del, and P be the probability space and X be a random variable defined on the sample space S, the function capital F R to R defined by f of x, here x is a random variable, is equal to probability of minus infinity to x semi-closed interval, whose left side is open and right side is closed. Then we define a function capital F R to R by f of x is equal to probability of minus infinity to x is equal to probability of that event which belongs to minus infinity to x, for all x belongs to R. Is it clear? If S, del, and P be the probability space and x be a random variable defined on the sample space S, then we define a function f R to R by f of x is equal to probability of minus infinity to x is equal to probability of that event belongs to S which assigned value by x belongs to minus infinity to x. This is capital Fx. This function is called distribution function or cumulative distribution function of the random variable x. Clearly, the domain of the function f is minus infinity to infinity, and we know that the probability of any event lies between 0 and 1. Therefore, the range of f is close interval 0, 1. Okay, let's consider some example. We consider the experiment tossing 3 coins. then the outcome sample space S can be defined in this way, that contain 8 elements. Then we define a random variable on the sample space S by the number of heads H. Now from our previous definition of probability of x is equal to 0, that is probability of the event which does not contain any heads. Which is the event? Which is that event? That event is TTT. And which is its probability? What is its probability? Its probability is 1 by 8. X is equal to 1 means the events that contain only one head. In S, there are 3 events like that which contain only one head. Therefore, probability of x is equal to 1 is equal to 3 by 8. And similarly probability of x is equal to 2 is equal to 3 by 8. And when x is equal to 3, that is all the outcomes I had, there is only one outcome. Therefore, probability of x is equal to 3 is equal to 1 by 8. Now we find what is the probability function, distribution function of x. Distribution function f was defined from R to R by f of x is equal to probability of minus infinity to x. When x less than 0, then fx is equal to then fx is equal to then fx is equal to this one, probability of minus infinity to probability of minus infinity to x, and when x less than 0, then there is no event, because x, the range of x is 0, 1, 2 and 3, and the interval minus infinity to x, when x less than 0, does not contain any values of capital X. Therefore, the event is impossible event. Therefore, probability of minus infinity to x when x less than 0 is equal to 0. This is why f of x is equal to 0 when x less than 0. When x belongs to 0 and 1, that is 0 less or equal to x less than 1, then f of x is equal to probability of minus infinity to x. Here, this interval contain only one values of capital X, which is 0, and this corresponding the event TTT, whose probability is 1 by 8. This is why f of x is equal to 1 by 8 when 0 less or equal to x less than 1. Similarly, when x belongs to 1 to 2, that is 1 less or equal to x less than 2, then the interval minus infinity to x contain the value of x 0, 1. Therefore, the corresponding events are for the value x is equal to, and when x is equal to 1, there is 3 event HTT, THT and TTH. Therefore, the probability of this the probability of the event minus when x belongs to 1 to 2 is equal to addition of these two probabilities, when probability of the event when x is equal to 0 and probability of the event when x is equal to 1. This is why f of x is equal to sum of probability of x is equal to 0 and probability of x is equal to 1, which is equal to 4 by 8. Similarly, when x belongs to 2 and 3, then the f of x is equal to 7 by 8, and when x get equal to 3, means f of that when x get equal to 3, we know that the range of x is 0, 1, 2 and 3. Therefore, when x get equal to 3, then the distribution function capital F of x is equal to probability of minus infinity to x, where x get equal to 3. This interval minus infinity to x contain all the values of x, that is, the event contain all possible outcomes of the random experiment, that is, the event is S, full sample phase, and we know that the probability of full sample phase is equal to 1. Therefore, f of x when x get equal to 3 is equal to 1. This is why when x get equal to 3, then f of x is equal to 1. Is it clear? Any question about distribution function? Can you hear me? Okay, we recap all these things. If we consider a probability space S delta P and x is a random variable defined on S, then we define a real valued function f r to r by f of x, where x is a random variable, is equal to probability of minus infinity to x. This is the definition of distribution function capital F. Then the domain of capital F is capital R, that is whole real number, and the range of F is close interval 0, 1. And here is one example of tossing 3 coins. Now we discuss about some properties of distribution function. We know that the probability of an event A, the values of TA lies between 0 and 1. Similarly, here also the values of the distribution function belongs to 0 and 1. Probability of the event X when X belongs to A to B, this is equal to f of B minus f of A, where f is the distribution function. This is the relation between probability and distribution function. F is a monotonically increasing property. It says that at the right hand side, that is f of infinity is equal to 1, and left hand side f of minus infinity is equal to 0, and f is also a right continuous function. This is a real valued function, and also it is a right continuous function. That is f of x is equal to f of x plus h, where h tends to 0. We have proved this. Proof of A. We know that the probability of an event belongs to 0 and 1. Also, we know that f of x is equal to probability of minus infinity to x, that is of an event. Therefore, the values of random distribution function lies between 0 to 1, as probability of an event lies between 0 to 1. Okay. Now the proof of B. Proof of B. The event minus infinity to A and the event when x belongs to A to B, these are mutually exclusive event, as there is no common point between these two events. Also, if we add these two events, then we get that the event x lies between minus infinity to B, as the events are mutually exclusive. The event x when x belongs to minus infinity to A less or equal to A, and x belongs to A to less or equal to B, as these two events are mutually exclusive, then we can apply third axioms of probability. Therefore, this equal, we can, this probability probability of minus infinity less x less or equal to B is equal to probability of these two addition of these two probabilities, that is p of minus infinity less x less or equal to infinity is equal, this is equal to f of A. This is the distribution function, and the right hand side is f of B. Therefore, probability of A less x less or equal to B is equal to f of B minus f of A, where f is distribution function. It is easy to show that f is a continuous function, because we know that f of x lies between 0 and 1. If x1 greater than x2, then also we have p of A less or equal to x less or equal to B is equal to f of A minus f of B minus f of A. Therefore, probability of the event where event lies between x1 and x2 is equal to f of x2 minus f of x1, as probability of the event x when x belongs to x1 less x2, x1 less x less x2, this is get equal to 0. Therefore, f of x2 get equal to f of x1. Therefore, f is a monotonic increasing function. Now we have to prove that f of infinity is equal to 1. For this, we consider the event capital An by An is equal to the event minus infinity less x less or equal to n. Therefore, this is a An sequence. An is a expanding sequence, because as n increase, then the interval also increase. Therefore, An is a increasing event. In our previous class, we know that for an increasing event, expanding event, limit n tends to infinity, An is equal to minus infinity. An is equal to union of An. Sorry, this result does not require here. Thus, we have a sequence of monotone of increasing event An, and limit n tend to infinity An is equal, from the definition of An, limit n tend to infinity An is equal to the event which lies between minus infinity and infinity, and this is the whole event. Therefore, if we take probability with, from the both side, we get that probability of limit n tend to infinity An is equal to 1, as P of s is equal to 1. From the definition of distribution function, P of An, that is probability of the event x, where x lies between minus infinity to n, is equal to Fn. This is the definition of the distribution function f. If we take limit n tend to infinity, then from previous line we get that limit n tend to infinity P of An is equal to f of infinity, because f of infinity is equal to P of minus infinity less x less or equal less infinity. From equation 1 and equation 2, we see that in our previous class we said that the probability and limit can interchange their position. Therefore, the left hand side of equation 1 and equation 2 are similar, and this proves that f of infinity is equal to 1. This line f of infinity is equal to 1. Similarly, we can similarly, if we consider a contracting sequence of event, then we can prove that f of minus infinity is equal to 0. Similarly, f can be proved. In the properties f was that f capital F is a right continuous function. That is f of x plus 0 is equal to fx. It is a trivial proof. I skip this. There is a theorem. We state this theorem. We do not prove this because this is out of syllabus. Therefore, we have to know this theorem only, not proof. The theorem says that if f R2R is a distribution function of some probability space, a function f R2R is a distribution function of some probability space if and only if satisfies the following property: f is non-decreasing, F is the right continuous, and f of minus infinity is equal to 0, f of infinity is equal to 1. We proved all these three properties previously, just previously. Right continuous, f of minus infinity is equal to 0, f of plus infinity is equal to 1, and f is non-decreasing function. That is, f is a increasing function. There is another theorem. The theorem states that let f be a distribution function of a random variable x defined on a sample space S del T, where S is the event space, del is the Borel field on S, and P is the probability. Then f of x minus f of x minus 0 is equal to probability of x is equal to 0. Sorry, x is equal to small x. X is equal to small x means capital X is a real valued function defined on S, that is some event, and x is equal to x, capital X is equal to small x mean the value of an event, say W, under X, capital X is small x, that is capital X of W is equal to X. And f of x minus 0 means limit h tends to 0, f of x minus h. For proof, let us consider that you consider the events minus infinity less x less or equal to x minus h, and uh, the event lies between x minus h less or equal to x, where h is a h greater than 0. Then these two events are mutually exclusive because there is no common point. Also, union of these two events is equal to minus infinity less x less or equal to capital small x. If we take probability, then by axiom 3, the probability of this union is equal to probability addition of sum of these uh, probability of these two events separately. Therefore, probability of x minus h less x less or equal to x is equal to fx, which is equal to probability of minus infinity less x less or equal to x minus f of x minus h. If h tends to 0, if h tends to 0, then f of x minus h is equal to probability of limit h tends to 0 x minus h less x less or equal to x. This came from the definition of distribution function f. This implies that f of x minus 0 is equal to probability of x at x. It is proof. There is another theorem. This is a necessary and sufficient condition. In a necessary and sufficient condition of a distribution function f of a random variable x to be continuous is that probability of x is equal to small x is equal to 0. The theorem states that a distribution function is continuous when probability of x at x is equal to 0 for all x belongs to R. True. We know that the probability distribution function is a right continuous function. We proved this previous. Therefore, we have to prove that this is also a left continuous function. Then the proof is done. For left continuous function, we have to show that f of x minus 0 is equal to fx for all x belongs to R, and this is equal to fx minus f of x minus 0. And from the definition of distribution function, this is equal to p x minus 0. From the definition of the previous theorem, f of x minus 0 equal to 0, and from the previous theorem, this is equal to probability of x is equal to x. Therefore, the necessary and sufficient condition of a distribution function to be a continuous function is probability of x is equal to 0. There is another example. On a random variable x, assume the value -1, 0, 1 with the probabilities 1/3, half, and 1/6 respectively. You have to determine the distribution function. Here the range of the random variable x is given, and the range is -1, 0, 1, and that distribution function or probability also given 1/3, half, and 1/6. Then we have to find the distribution function. The definition of distribution function fx is equal to probability of -infinity less x less or equal to small x when x belongs to -infinity to -1, -infinity less x less -1, then this interval does not contain any values of capital X, as the range of capital X is -1, 0, 1, and x less than -1. Therefore, the probability of -infinity less x less capital X less small x, where small x belongs to -infinity to -1, then the probability of that event is equal to 0, because there is no values of capital X. Therefore, when x less than -1, capital F of x, that is distribution function capital X, capital Fx is equal to 0. When x belongs to -1 less or equal to x limited to -1 contain one value of the random variable x, which is -1, and the probability of the event -1 corresponding event -1 has probability 1/3. It was given. Therefore, the distribution function fx at when x belongs to -1 to 0 is equal to 1/3. Similarly, when x belongs to 0 to 1, then fx is equal to sum of the probability of x is equal to -1 and the probability of x is equal to 0, which is 5/6. And when x belongs to x greater equal to 1, then the interval contain all the sample point of the event. Therefore, capital F of x is equal to 1, because this contain whole sample point of that random experiment. This example says that when a random variable is given, the range of the random variable is given, and the probability of the corresponding events are also given, then we can find the distribution function of the random variable as below. There's another example. This is a home task. In our next class, we discuss about expectation.